ראית שתיקנתי את זה?
כן, כן. אני... כן.
אתה כן?
זהו, פשוט שינית את המינוס לפלוס, כאילו, נכון?
לא שיניתי את המינוס לפלוס. הקטע הוא שלא עשיתי שם את האינטגרל בזהירות. שם האינטגרל על 1 חלקי I אומגה מינוס אפסילון K. נגיד D אפסילון. כפול מיו. אז הדבר הזה הוא נותן כאילו נראה לי, כאילו לא יודעת אם אני טועה, הוא נותן משהו כזה ולא הפוך כמו שאמרתי מקודם. אולי אני טועה. כאילו יש שם איזה בלבול עם זה.
אוקיי. וזה הפוך מה שכתבנו פה?
אני לא יודע, תסתכל בנו. לא, זה נתן, הקטע הסופי זה שסיין של אומגה ממשיך אנליטית לאחד, ושהביטוי הזה נותן מינוס I ניו פאי כפול סיין של אומגה. בגבול שאתה לוקח את הלמדה זה ליצור.
כן. כן.
אוקיי?
אבל, אגב, יש לך, כאילו, זה שיטה הפוך.
מה?
יש לך שיטה מעניינת לעשות, כאילו, המשכה, אתה מחליף את I אומגה באומגה ועוד I אטה.
I אומגה? זה שיטה מעניינת.
מה?
זאת השיטה.
עכשיו,
לא. אוקיי, שנייה, תכף אני אסביר לך. אתה עושה את זה. זה בהגדרה המעבר שלנו מ-response functions שהם מצובר ל-response functions שהם... ג'וסף מצטרף או שהוא לא...
אתה אומר זה ההגדרה.
לא. כשאנחנו אומרים המשכה אנליטית, אולי אני אדבר באנגלית, when we say analytic continuation, we're not talking about, you know, when you tell a mathematician analytic continuation, it's just taking some analytic function or a function in some region and assuming that it's analytic and continuing it to a larger region.
Yes.
Specifically for us, it's different. We can calculate response functions over these special points along the imaginary axis, which are known as Matsubara frequencies.
Yes.
It's very easy for us. It's much easier than doing it elsewhere. And the analytic continuation that we're talking about is obtaining a function of these Matsubara frequencies and continuing it specifically to the real axis. That's the point. So when we say analytic continuation, that's what we mean. So you can view this thing like a wick rotation, but it's a wick rotation plus a small deviation.
Down or up?
Down.
Down?
Down, because we said that any response function, in order to be causal, needs to be analytic in the upper half.
Okay. In the retarded version. Yeah.
The physical, yeah.
Okay. Retarded. Yeah.
Zvi was asking me about the analytic continuation, so I actually added a note to our webpage about something which is, you know, I didn't encounter anyone ever talk about it, but people always do that. I would say that even in most cases that we want to do analytic continuation in condensed matter, we're analytically continuing non-analytic functions, which, you know, yeah, there's a limit. Come on, guys, this is that's not okay. So the question is, how do you analytically continue? Because then it gives these kind of funny things that like sine of omega analytically continues to 1. Like, what on earth does that mean?
Mm-hmm. Right.
So what I suggest, and I wrote a note on that, is to remember where did this sign come from. Because anytime we get these non-analyticities, they actually come from, okay, so first of all, they come from a continuum, which gives a branch cut. But then it typically comes from, taking some cutoff to infinity. So what I propose is don't take this cutoff. Leave it this way. Analytically continue this, and then take the cutoff to infinity.
Right, okay.
And that provides you a scheme of making sense of this mess.
Okay.
Okay? And then you're only dealing with analytic functions, and everything is nice. Well, they're not analytic, everywhere. They can have these branch cuts. But the whole point is that these branch cuts are lower than or below the upper half plane, and they don't bother us.
Okay.
And why the values of the functions that we're computing are only in Mitsubara frequency, like I omega, not in omega?
It's not only. You can do these calculations in real frequency as well.
Yeah.
But it's just easier with Mitsubaras. I'll give you an example. Okay, let me take you back. I always like to joke and say that you like Peskin. But seriously, if you read Peskin, he does all these integrals, right? He's calculating, he's using this Feynman. We didn't learn this. Maybe
Feynman parameters or whatever.
It's called Feynman parameterization. Maybe I should also put that in your exercise.
Fortunately, we didn't learn it.
No, I could put that in your exercise.
Okay.
It's actually a neat trick. Maybe I'll write a final exercise, which would be some extreme thing.
Oh, no.
Anyway, the point is that when he does all these tricks, one of them is to switch to Euclidean space.
Yeah.
Why? Why does he do that? Why does he bother? Why doesn't he do it in real frequency?
Because then it's compact.
It's compact.
Like.
You think just because he can write it as a vector?
Yeah, maybe it's easier to do the integral.
It's easier to do the integral. That's the point. So it's easier to compute things in Matsubara space. In particular, you don't have divergences. Actually, this becomes even more important when you're doing things numerically. In Matsubara space, everything is easier. Nothing diverges. There are no resonances. Okay? So that's very convenient. But the only price you have to pay is that then you have the headache of analytically continuing it back. Okay. And that's not always a trivial task.
So it's like on the line, imaginary line. It's not just Matsubara points.
Well, that depends. The lower your temperature is, the more dense these points are going to get, and at temperature 0, you're going to get a continuum. But in many practical cases, like solving the Eliashberg equation, like we do sometimes at finite temperature, or when you do quantum Monte Carlo, DMFT, all these things, you always in the end get a grid. You get a set of points. And then it's even more challenging. And there's a theorem. Okay, there are theorems about analytic continuation, and it turns out that if you have the value of an analytic function, there's only one analytic function that goes through an infinite set of points. If you take an analytic function and you sample it at an infinite number of points, then it's the only analytic function that would, go through all these points.
Because it's an infinite polynomial.
Yes. But if you truncate it, no one ensures you anymore that it's unique.
Okay.
So one of the big issues is what is the analytic function, because we never have the infinite series. We always have a finite set of points. That's like a big challenge. Yeah. Then So let's say, so today what we want to do is
I actually have another
Yes.
this kind of questions.
Yes.
So it seems like in like when we calculate sigma or the green function, we have I omega. But usually when we have a Fourier transform, we don't have this I. I understood that you want like this. When you wrote the equation for sigma, you said sigma I omega equals to sine omega or whatever. But you have sigma I omega, not sigma omega.
Are you asking about, writing it like this?
Yes.
This is just a convention because,
Okay.
this is like writing a function of something.
Yes.
And actually, I guess I was kind of sloppy when I used this, because what people really mean when they write this is, so for example, if I would write g of I omega and k, and this thing is equal to I omega minus epsilon k, then they're actually thinking, so that this function, if I would write here z, then this would be z.
Yes.
That's kind of the point. So it's kind of thinking about this as already as an analytic function over the entire upper half planars. Just a notation. But I agree with you that it's confusing because sometimes it matters. Because, for example, if you would write something like this, and then you would have, now let's imagine that this is like a bosonic propagator. So you could have something like, omega squared plus ck squared. Then it's not exactly a function of I omega, right? So we need to remember that this thing is actually I minus and squared, right? And then, if you would analytically, so if you write something like this, and now we want to write it as z to analytically continue it, then this actually becomes minus z squared. That's something you need to remember. Do you understand what I mean? Not really.
It was I omega. And then
Again, let's assume you have a bosonic propagator. Let's even call it d. Okay? So let's say you have d of omega of I omega and say some q.
Yeah.
Typically in Matsubara space, if it's like a Gaussian mode, a typical thing, then you'll have here something like omega squared plus cq squared. But if I want to think about this as analytically continued and write here z instead of I omega,
Yes, then you get me.
then you need to remember that there's a minus. That's the only point.
Okay.
Okay? So that's why people write it like that. Okay?
Yes.
Okay, so now what we want to do is we want to do our G of fermions, and in the end of last class, what I was so first of all, for simplicity, okay, so maybe I'll remind you a little bit about the RG. Reminder. Wilsonian RG. So in Wilsonian RG, what we had is we had some fixed. So okay, so first of all, we had momentum space. We had some momentum space. Let's say this is K2 and this is K1, and this can also be include frequency or whatever you want. And then we define some sort of cutoff. Okay, so this is like a shell of radius lambda, and then we have S0, like our action is like S0 plus S interaction. Then we define a thin infinitesimal shell of width lambda times b minus 1, right? That's the size of this tiny shell. We integrate it out. We define these as fast modes and these as slow modes. we integrate it out. So let me write. So we have S is equal to S naught plus S interaction. So integrate out fast modes, and then we get a new theory, right? Like where we eliminated the thing, and now our cutoff is lambda over b. So in order to complete the RG transformation, we need to stretch this. Okay, this stretching, this integrating out the fast modes is like coarse graining, and the stretching helps us bring the action back to its original form. So when we did that, we found this relation. Let me write it. So we basically define, S slow prime before the stretching as S0S plus S interaction SS. So we keep only the interaction part that scatters within the slow modes, and then this gets corrected by this guy. And where this expectation value 0 is computed within the fast modes. That was the technique of the Wilsonian RG that we found. And then it's all a question of whether you can compute this, what order you compute this, but whatever you can get, like the expansion of the beta function and so on. Now, if we look at the fermions, the problem with fermions is that we have a finite density of them. By the way, this problem would also appear in bosons if we would have a finite density of bosons. Same problem, more or less. I don't actually know how you would solve it for bosons. That's another question. It's also difficult.
What do you mean by finite density?
Okay, I'll explain to you. So these kind of theories, like a phi to the fourth field theory that we did it on, it's like phonons or photons, or the number of particles is not conserved. You can see this because the phi field, right, goes like A plus A dagger, right? And its conjugate momentum goes like A minus A dagger. So in the beginning of the course, when we did the, Noether's theorem, right? And we looked at the current, we saw that these field theories, they don't have a conservation of number of particles, right? That was actually one of the issues with quantizing it. So we understood that the right way to quantize it is to
Quantize the field.
no. So what we did was, we diagonalized it, and then we wrote the field theory in terms of what you call them, coherent state,
Right.
Right? The creation and annihilation operators, and and then we got, the well-defined, let's call it, quasi-particles. But the point is that they're not. Why am I saying that they're not conserved? Well, it depends. It depends on what theory you're exactly writing. But in principle, they're not conserved, and this is important because then the self-similarity is not a problem. Because let's say you have a finite density of particles in space and they're conserved, then obviously, if you coarse grain, like you double the size of your element, your length element, and then you kind of shrink space or stretch momentum to make it self-similar, then the density will change, and that's a problem for us.
Yes.
Okay. So, and in particular for fermions, what we have, let's assume we have some parabolic dispersion, then we have some Fermi energy, and we have the corresponding Fermi surface. Fermi surface. Kf, and this is not the same shell like here. First of all, this is so basically, like, there's a question. So we could naively do the same thing. We could like maybe say, okay, let's put a cutoff above this Fermi energy, this Fermi surface, and then just do the coarse graining until we reach the Fermi surface. But that would introduce a number of problems. First of all, it would change the density. That's like the biggest problem. Another problem. Another problem is that it would not treat the elementary excitations around the Fermi surface on an equal footing. For example, we know that we can introduce holes by exciting particles to high energy, and we're not taking them into account. We're only taking, some energy states above the Fermi. So the question is, how do we do the procedure in this case? And what I was about to say is that the solution is known as Shankar RG. Although I've heard numerous people complaining about the fact that this was known way before him, doesn't matter, I don't care that much about credit. So the idea would be, imagine that our Fermi surface is this dashed line is the Fermi surface. Okay. Then I introduce the upper and lower cutoff above and below the Fermi surface. Okay. So we have, let's say this is 2 times lambda, and then this guy is like Kf. So we have 2 shells at, the outer shell is like Kf plus lambda, and the inner shell is a radius of Kf minus lambda. And this will be our theory, basically, okay? And what we're going to see is that it's a mess, like in general it's a mess, but asymptotically, you'll understand what I mean in a moment. Asymptotically, in the limit where this thing goes to 0, which means that I'm really closing in on this Fermi surface, then things start to become universal. Then I get well-defined RG transformation, and I can discuss everything in a controllable way. And the reason this is fine is because I want to remind you that in a typical metal, the Fermi energy is like 100,000 Kelvin. Okay, so it's not a problem for this cutoff to be much, much smaller than the Fermi energy, but still in a temperature range that we're interested in. So we can look at low energy, low temperature, kind of long wavelength phenomena, which is all occurring kind of around this Fermi surface. It's good for us. It can capture a lot of phenomena that we're interested in, actually most of it, and still be universal and well behaved. Okay, so now let's write a theory. Okay. So now let's write the free part and the interaction part. So the free part is just an integral from minus infinity to infinity d omega over 2 pi, an integral from minus lambda to lambda dk over 2 pi, and an integral over the angle 2 pi d theta over 2 pi. And there is some kf factor which I'm absorbing into the units of s, no? And then I have here omega minus, let's say, v of k, okay, times psi bar of k omega and theta, or maybe let's write it there, omega k and theta. So I have omega k and theta. Okay, so that's the free part. צריך לנעול פה את הדלת. משגעים לי את השכל. And the interaction part, we're going to write like this. We have j is equal to 1 to 3. The integral from minus infinity to infinity d omega j over 2 pi, the integral from minus lambda to lambda dk j over 2 pi, integral from minus from 0 to pi d theta j over 2 pi. Then I have a theta function of lambda minus k4. And then I have u of 4, 3, 2, 1, which is almost like the secret code. U of 4, u bar of 3, u of 2, psi of 1. Okay, so the first of all, you can identify that here we have only 3 integrations, and that's because we had delta functions coming from conservation of momentum and energy as usual. But the only funny thing, and this is some generic interaction between these 4 momentum. The only thing that is, and I must say that we are implicitly assuming, right, that K4 is actually a function of the other K's. So here I need to make a definition. Before I write K4, let me make a definition that we have, a Pj is something like Kf plus Kj times Nj. So Nj gives us the direction, and N, maybe I can even call it N of theta j. So N is like an arrowhead, it's a unit vector pointing in the angle theta j, and the magnitude is exactly Kf plus Kj. So that gives us Kj is kind of relative to this momentum. So that implies that K4, okay, is basically I have an expression, let me not make any mistakes. So it is, we can write it as Kf times delta plus K1 N1 plus K2 N2 minus K3 N3 minus Kf. So what you have here, okay, and this delta here, this guy, delta, something I'll use later, is something I define as Kf, sorry, it's N1 plus N2 minus N3. Just a vector, some vector, which maximum value is 3, minimal value is minus 1, I don't know, or minus 3. In any case, this K4 is the small piece of P4. Yeah. Now, what did I want to say? Okay. Now, the important thing here is that, okay, these guys are all small. Okay, because I'm integrating over them, and they're between minus lambda and lambda, and we're in this limit. So I don't have any fear that these guys are going to make K4 particularly large. But if I want K4 to also be small, I'm in danger with this delta. Because like I said, this delta, for example, I could have N1 and N2 pointing in the same direction, and N3 exactly opposite to them, and then I'll get 3. Okay, I'll get a vector of, a vector with size 3. So it's going to be Kf times 3. It's like 3 times Kf. It's going to be way, way out there. I even have a drawing in my note. I'll try it to give you some intuition.
It's actually a factor 6, right? Because there are also the other vectors there. K1, K1.
This one? No, that's the point. K1, K2, and K3 are integrated over this small deviation. They're tiny. They're not going to influence anything. They're not my source of concern. So, for example, you could imagine this being our Fermi surface, and then say P1 is here, P2 is here, and P3 is something like this. Then you'll find that P4 is like way out here. So, if this is Kf, then this size is K4, and that's way bigger than Kf. Now, how do I compute this? Because I need this sum of these two to be equal to the sum of these two.
Which two?
Did I do this properly? No, maybe not. Wait a second. So the sum of these two is a vector here. So I need to correct this a little bit. So now I need a vector that I go here, and then I need to go. So let me explain. Okay, you understand though what I'm saying, right? Because this is like this, I guess. This is like P1 plus P2. And now I need this guy to give me the same thing. So I need to go from here, so it's like this. Okay? So this is like P4. Okay. So then this guy is like K4, and it's even larger than Kf. So that's a problem. So what this theta function does here is make sure that K4 doesn't exit that regime. That's the point. So it's kind of confusing. Now, so now let's think about RG transformation. So let's imagine that we want to change the cutoff. So we integrate out the fast modes, and therefore we have lambda goes to lambda over b.
Okay, can I have a question?
Yes.
If K4 is much larger than
Kf.
Kf, even Kf plus lambda, so why do we have this heaviside function?
Again, I think you inverted the logic.
Okay.
The point was that, you know, we want to think of a theory that only lives on this shell here.
Yeah.
That's what we're doing. By the way, the philosophy behind this is that everything outside this donut, we integrated over. So this is an effective theory that you obtain after you integrated out everything outside it. Now it's very complicated to do that, but we assume we did that. Then we start with a bunch of parameters which we will consider to be phenomenological. And then we can say something universal in this regime. So now to answer your question, that means that all four momenta have to lie inside the donut. What I'm saying is that naively, you know, I could just assume that K4 is given by the delta function of conservation of momentum, which is this equation here. And, you know, just write the interaction like this, like you usually do. Okay?
Yes.
But the problem is that you see that even if you allow K1, K2, and K3 to be on their allowed values, you can easily reach a situation where K4 exceeds its allowed value.
Yes, okay.
And that's why we have this theta function. Now, this theta function introduces a problem for us because now the RG transformation becomes ambiguous. Because imagine that we integrate out the fast modes, and now we want to move to a different cutoff and re-stretch. Then we have a problem because we want to say something like theta of lambda minus K4 is equal to theta of lambda over b minus K4, which is equal to theta of lambda. Like, what I'm trying to do now is I'm imagining that I'm doing the rescaling. So I don't have a problem with these guys. We've already seen how to rescale it. This is just an interaction. We're going to do the usual thing and throw away the irrelevant k dependence and whatever. And these are fields. So the only guy that really gives me shit, let's put it that way, is this guy. So I want to take care of him. So I want to understand how to do that. So I'm imagining, oh, sorry, I didn't write this properly. So what I'm imagining is that I'm changing from theta of lambda minus K4, I'm changing to theta of lambda over b minus K4. And this guy I can write as theta of lambda minus bk4. That's the same thing. And now I'm going to try and absorb this inside the definition of K4. But you see from the expression for K4 here, okay, that there's no problem here if I absorb it in these Ks. Okay? That's not a problem because we're going to make BK, right? The transformation that we want to do, maybe I'll write it here, is this plus K BK equals K prime, right? So when this b multiplies these k's, they just become k prime. But the problem is that kf changes its value. Again, the same problem we had before. So we get kf, we get basically, we get lambda minus b, we absorb the b inside. So we write something like k4 of k1 prime, k2 prime, k3 prime, and bkf. So that's a problem for us.
K4 is also prime.
What?
We also change to K4 prime. No?
This is the prime 4.
Well, it doesn't matter. That's a question of, what do you even define? But K4 is not a parameter.
Okay.
It's a function of the other K's.
Yes, that's right.
So if you like to call this K prime because you've changed everyone inside to K prime, that's fine. But I don't want to do that because it's actually the exact same function it was here. I can actually call this K4.
Yes, you're right.
Okay? This is K4 of K1, K2, K3, and Kf. Okay? That's what it is. Now, I don't want to change anything. I just want to comment that following this restretching, I didn't arrive with the same theta function. I have a problem. Okay?
Okay.
But we notice that this problem is eliminated under a specific condition where what is the specific condition? Hold on one moment.
Why is it a problem that we don't have that?
Well, it's a problem because the whole point of the RG is that we want to, integrate out, okay, then restretch. This is the stretching part, okay, and then after we stretched, we want to bring everything back to the original form, and then we can identify a mapping between parameters here and parameters there. But this b here is what gives me a problem. Because it doesn't allow me to go back to the exact same form.
Can you change parameter?
What?
Can you just change the parameter?
Yes. Okay, now I remember. What was the question?
Can't you just change variables? The integration.
No, but the kf is not a variable of integration.
Okay, yes, I understood. And it can change.
First of all, we don't want it to change.
Okay.
But if you want to talk rigorously, it's you can define an RG transformation any way you like. But basically, what you're doing is, if you allow your Fermi surface to change, you're basically flowing in the space of metals of different density. That's not what you want to do. You're looking for something that
maybe this density changes in different scales, like the mass or.
Yeah, first of all, it's very confusing to understand what this RG actually means. Because it's not coarse graining like you do for the fight of the fourth field theory. It's not straightforward. And it's very problematic, to be honest. And it raises a lot of questions which I think we still don't completely understand today. But this is a technique that has been developed. It's the leading approach, and therefore I'm teaching it. But I think that from the viewpoint of a mathematician, we want to define a closed circle in which we come back to the exact same form. So I think I have all the right to complain that, you know, this is not good. This is not good enough. I want to get rid of this. But I want to argue that there is a limit where this happens. There's a limit, you know, if I neglect, okay, so I can write in general, this is a problem because we didn't come back to the same form. But there is one limit where this kind of magically disappears. There is a specific, let's call it specific case where the problem disappears. And that's the limit where delta goes to 1. So when this vector becomes of order 1, and lambda is much, much larger than the kj's. Okay, so if we think of the upper cutoff as something large, and these k's being some low energy compared to lambda, so now we have a whole hierarchy of energy scales, right? Lambda is much smaller than kf, but much larger than these small k's. Okay, then you see that this k4 is of order 0. So we basically want to ask, when is delta equal to 1? And it turns out that there are actually 3 cases where this works. Okay, so the 3 cases, there are 3 cases. So the first case is when theta 1 is equal to theta 4 and theta 2 is equal to theta 3. Second case is when theta 1 is equal to theta 3 and theta 2 is equal to theta 4. And the last case is when theta 1 is equal to theta 2 plus pi and theta 3 is equal to theta 4 plus pi. Okay, let me make some drawings to explain this point.
I think in each case, because of quantum conservation, you get one of them from the another one.
Yes. Totally. This I'm putting in Sograim.
Parentheses.
In parentheses. Putting it in a parenthesis to denote exactly what you were saying. If theta 1 is equal to theta 4, that immediately implies that theta 2 is equal to theta 3. So the point is, you can imagine that initially, you know, this is like n1 and this is like n2, and then you end up with n4 here and n3 here. Okay, so basically you have some very small scattering in the same direction. The other option is where you have n1 here, n2 here, and then N3 is like here, and N4 is here. Here we can think about this as some sort of exchange, where this basically scattered to here, and this scattered to here. And the reason I'm calling it exchange is because I'm imagining, you know, when we write a vertex like this, one, two, three, four, okay? We can always interpret this as some sort of bosonic mode that mediated it, like a density-density process. So in this kind of interpretation, you can think about this as a process like this, and this as a process like this. Something like that.
So it's kind of a Hartree-Fock, like Hartree-Diamond.
It's it's related, but it's just these are the channels of the Hartree term and the Fock term.
Okay.
Essentially. And then the last one is the special case where the total momentum incoming the diagram is basically zero. So it means that these N1 and N2 cancel, and therefore N3 needs to cancel with N4. So we have something like N1 and N2, and here you can basically scatter to any N3 and N4. So this would be a scattering like this, where this scatters to here and this scatters to there. Okay?
This can also be the one.
What?
This can also be a drawing like the other one. It can the two ones, then a boson, and then.
Yes, yes. This one, we totally, but the difference is, this one we would typically want to. Okay, so let's draw it like this. This one we would like to draw something like this. It's more convenient to draw it like this, because we have the two incoming come with 0 and the two outgoing come with 0. But by the way, everything when I'm saying 0, I mean it's very similar. So then this would be like 1 and 4, and this would be 2 and 3. And but it's not really different. It's the same thing. It's just yeah, I don't even know what it matters. Okay, never mind. But the point is that when I say 0, everything is 0 up to these k's. Okay, these k's are considered small. And people, so in Shankar's notes, he calls this 0 sound. This is 0 sound prime, and this is BCS. But like you said, these are like forward scatterings in the direct and exchange channels. So we can also write direct channel, exchange channel, and BCS remains BCS. And he calls it 0 sound and 0 sound prime because when you calculate in Fermi liquid theory the 0 sound mode, then these kind of processes are important. actually, sorry. No, I take it back. Erase the zero sum. The zero sum corresponds, I think, to a diagram at one loop order. Let's just call them direct exchange indices. Okay. So now
there's also high energy, if you want. We talked about.
There's also what?
An high energy name for these channels, which is U, T, and S channels.
U, T, and S. I couldn't care less.
We just
Okay, so let's see. So now what I wanted to do was to give you another So I wanted to give you some interpretation. Okay. So there are a few interpretations. Okay, so in my notes there are at least two more explanations. Okay, about why these three channels are the important ones. The first one gives you a kinematic explanation where you kind of draw the allowed momenta visually, and you can show how these angles are kind of constrained to be equal to each other. And the second one, which I think is the most rigorous, like nicest way, is to change this theta function to become a soft cutoff, like an exponential cutoff. And then the nice thing about that is that you can really absorb it into the RG transformation. Actually, the last one I think is nice. It kind of explains it the best. So I think I'm going to show that. And then after we explained all this and we're satisfied with the thing, basically the bottom line is going to be that from the original interaction we wrote, there's actually going to be only these channels. And they're the only thing you really need to renormalize. Because everything else, I'm going to show you in a moment, that basically this interaction, which was a lot of momenta, a lot of possibilities, after RG transformation, all of them disappear very, very rapidly, except these specific cases. They're the only ones that kind of survive the RG transformation. That's basically the argument. And therefore, what we actually want to renormalize in RG are these channels. So we get these three channels, and we want to renormalize them. So we basically have three parameters for the interaction, and that's all, instead of an interaction that depends on a lot of momentum. By the way, another comment that should be mentioned is that because we have a finite Fermi surface, we have all these angles, then it's not simple like we had for the bosons, where we could say, oh, let's expand it in K and then throw away the irrelevant terms. Because the angular dependence is not something you can throw away. It's not something that rescales with RG or something. So that's basically the point. How are we with time? So maybe we go for a break. After the break, I'll show you this thing, and then we'll do the actual RG and talk about some superconductivity and stuff, and the Fermi liquid theory. Yes.
In this limit, it doesn't mean that K4 goes to 0.
Only if you take
No.
lines to actually.
To what?
Only if K1, K2, and K3.
Yeah,
is
these
actually 0.
yeah.
But they are not actually 0. Just 1.
But then you have, then you still have Kf in the denominator. Oh no. No, okay, fine.
It's
Okay,
you get some negligibly small piece
Okay.
again, and then yes.
So if I would look to the symmetries and I would start with some symmetry in the interaction, then this would induce to look only to a small part of that symmetry and to blur out all the things that doesn't respect this interaction.
Can you give an example of what you mean?
I don't know, if we start with a O3 kind of problem, then if all the interactions in O3 that doesn't respect, they will blur out during the RG, and I don't know.
Don't respect what?
These symmetries.
Condition. These are not symmetries. This is not related to symmetry. It's related to kinematics. It's related to the fact that we're stuck on a shell and we want everything to stay in that shell.
But we're inducing some sort of symmetry in the momentum, right?
No, symmetries are of course important. I'm not saying that symmetries are not important. They can affect all sorts of stuff. But this specific thing is not related to symmetry. So it is true. You're probably right that we'll see we'll see as we continue where symmetry could jump in, show up.
Okay.
So let's get back here at 420. אבל איך זה יכול להיות רלוונטי ל-high energy אם אף פעם לא חושבים על finite density?
אני חושב, כאילו, פשוט מה שקיבלנו פה זה שלושת הדיאגרמות המסד הראשון של שני פרמיונים. שנכנסים שני פרמיונים ויוצאים שני פרמיונים.
לא, הציורים האלה זה בסדר. אוקיי? אבל ההבדל, what's special here is that they all have to be on Fermi surface. And that implies that the difference is that all this kinematic constraint won't exist if you have, if you're thinking about Dirac fermions, for example.
Yes, of course, in high energy you don't have these constraints, but you have these channels.
Yeah, that's true.
Are they the same channels? This is what I don't understand.
It depends on how you define.
I mean, it makes sense that there are only 3 channels. That's okay, but
the point is that if you have a small, let's imagine that you have a Dirac point and you have a cutoff lambda. Okay. Then you can have as long as you conserve momenta, you can have small k's all over the place inside that thing. Okay. And the angles, for example, can vary completely. Here, this angular constraint is something special to Fermi surface. Okay, that's all I'm saying. But you can still try to divide processes into let me think about it. Let's not waste too much time on this. But I think I think you can still define BCS like scatterings and
yes. And the way you do it, just look at your options to
conserve moment. Yeah, to contract
the fermion fields.
Oh, that's a different thing. That's true. That's true.
There are 3 options.
We'll get to that, but that's you shouldn't confuse between these constraints I've described and the diagrams. You have these kind of diagrams, something like this. We'll do that in a moment. Okay, so I just wanted to quickly say that another more rigorous view is to define a soft cutoff. Okay, so we can move from theta of, say, lambda minus k4, we can move to some exponent e to the minus k4 over lambda. Okay, and if we define this, then you can write the interaction term as pi j equal to 1 to 3, you know, all the integral over, say, omega, theta, and k, j, I'm writing it right here, and then we have e to the minus kf over lambda times delta. So again, we're neglecting the small k's, and then this becomes, this is not surprising, this becomes, the cutoff is delta needs to be equal to 1, as we've seen before, and then we add this u of k theta, psi bar, psi bar, psi, psi, say 4, 3, 2, 1, and then this goes to pi j equal 1 to 3, same integral omega prime j, theta j prime, kj prime. Imagine that I did this RG transformation. I'm going to get the same issue here. B kf over lambda delta minus 1, like this. And then I have, say, u of u prime of k prime divided by b, omega prime over b. We don't have a problem with this. I have psi bar 4, psi bar 3, psi 2, psi 1. Okay? Let's say like this. And the point is that this factor I can now rewrite as e to the minus b kf over lambda delta minus 1, I can write as e to the minus kf over lambda, which has the same structure as before, times e to the b minus 1 kf over lambda delta minus 1. So then I can conclude from this that my RG transformation for my interaction would be something like u prime. Oh, this is not u prime. So this is not u prime. But the point is that I will interpret u prime of k prime omega prime as being e to the minus, this is a minus b minus 1 kf over lambda delta minus 1 times u k prime omega prime. So I basically absorb this exponential in the RG transformation. And that implies that the only RG transformations that behave the way we want them to, where we can interpret, you know, u prime with the corrections connected to u without any funny business from the exponent, is really when delta is equal to 1. So all the other ones just very quickly become very small under RG. That's the more rigorous way of thinking about it. Okay, because you can think about this as a small dl, right? So it makes it irrelevant at tree level with a huge parameter kf over lambda. So it's basically just dying very, very quick.
Yes. It's not about I don't know what. Just about the calculation.
Yes.
So you have a U of k prime and over p, right? So you needed to change variables.
Well, what I did here, in going from here to here, I did two things. One of them was integrate out the fast modes and then stretch.
Yes.
So here I'm only thinking about the stretching part, which is the one that was problematic. And I'm looking at the soft cutoff, how it affects it. And then this helps me. The soft cutoff is a more rigorous way of doing stuff because now I can easily bring it back to the original form and think about this piece as something that is absorbed into the normalized interaction. And what it shows me is that basically for all the possibilities of scattering, it's fine. You get a well-defined RG transformation. They just go to zero very quickly. So they're very, very irrelevant, these scattering processes.
But what I ask is that there you have U over k tag.
It's going back to your question about the I and its functions. I just if you don't like it,
it's a little fun.
Okay.
No, but on the other side you didn't have.
What is the other side?
Like
this is the dark side of the moon.
Oh, I think you need
the other side of what?
No, when you compare what you are doing, you're comparing it to like the same.
First of all, the dependence of U on these momenta is unimportant because that part is exactly going to be less relevant than the zero limit. So if you're concerned about this, you can throw it away. But if U depends on momenta and frequency, let's assume for a moment that it does, okay? Then this dependence, all I'm saying is that, you see, here, moving from here to here, I need to do two things: integrate out and stretch. Okay? So when I stretch, I make a change of variables. You see here I have omega, theta, and k. By the way, there is no such thing as theta prime. Omega prime and k prime, I switched variables. When I did that, that changes here in the dependence.
Yes.
Okay? So this 1 over b here is just to remind us that we made a transform. So this thing,
Okay.
when I write here prime, like the total transformation includes also this fact. That's all I'm saying.
And you absorb like the b constant into the phi primes, right?
The b constant I absorb
When you change variables.
these guys.
Yes.
Yeah, I didn't write that yet. We'll do it now. That's like the tree level RG. You're right. There is some factors of B here, also from the.
Yes, that's what I asked.
Okay, we're gonna do that now. All this was just an argument to explain that you can make this more rigorous. Now, not just say, oh, it's small, or kinematically it's not allowed. You can actually write an RG. You can think about this U as like having an infinite number of channels, and then all of them being very, very irrelevant under RG. And the closer you are to these thetas, the longer they're going to survive this term.
Okay.
But as you asymptotically go to zero, eventually all of them become irrelevant except for these very specific conditions. But now let's do what you just asked for, more rigorous.
But maybe for that, like the soft cutoff is basically approximating the Fermi-Dirac statistic in a different way, like with an exponent instead of
No.
So how can you change the theta function with an exponent? Decaying exponent.
It's just another method, right?
It's what?
So when you define a cutoff, you absorbed my. We started the lecture on RG last time, where I just told you, okay, let's take a bosonic theory like phi to the 4th field theory. Okay? Now let's define a cutoff.
Yes.
that went, you know, through. You didn't even stop.
Of course.
But now suddenly you're complaining.
Maybe I didn't want to complain. But I internally complain. Well, I want to see what happens.
You internally complain. So the point is that when we define a cutoff on a
Yes.
theory, there are different ways of doing that. We hope that whatever result we get doesn't depend on the way we make the cutoff. When it does, we're very concerned.
Yes. Okay.
Okay?
Yeah. Okay. That I'm familiar with. Also, you approximated K further, right? You did assume that N and Ni are small, Ki are small.
Yes, I assume, definitely. No, throughout, we're going to assume the following hierarchy.
Okay.
Kj is much, much smaller than lambda, which is much, much smaller than K. Okay? Now let's do the tree level RG. So let's start from S0, which is our fixed point. S0 is our fixed point. This is our Gaussian fixed point. So we're doing right now RG around the Gaussian fixed point, which we will soon discover is not the Gaussian fixed point, but the Fermi liquid fixed point. Okay?
Mhm.
We'll see that in a moment. Magic, magic.
What's Fermi liquid?
You'll
Like
see
the
in a moment.
Lagrange?
What?
Okay.
Okay, so if you won't ask too many questions, I might get to the end and maybe you'll get a slight grasp of what I mean by Fermi liquid. But what we do now is we integrate out the fast modes, right? And we get and we stretch, okay? So we're going to get something like an integral from minus infinity to infinity, the omega prime over 2 pi. And then we get 1 over b from the omega. We have an integral from minus lambda to lambda. We get the same minus lambda to lambda because we stretched. But we have dk prime over 2 pi with a factor of 1 over b. Then we have here a factor of from 0 to 2 pi, d theta over 2 pi. And the point is that d theta doesn't obtain a factor of b. This is crucial. It makes all Fermi liquids the same. It doesn't even matter what their dimensionality is. 2, 3, 4, 5, 6.
Don't you miss like KF from the Jacobian?
Yeah, that I absorbed into the definition of
Ah,
reaction.
okay,
It's
okay.
not that, it's a units
Yes,
issue.
yes. Okay.
But amongst friends, the units of KF is 1. Okay? And then this guy gives me another factor of 1 over b psi. So we get here 3 factors of b.
Right.
Okay, so if we want to maintain this as a fixed point, what do we need the units of psi to be? 3 halves. So I apologize for the misuse of the word of the letter eta, because when we were talking about the bosonic field theory, then eta was the anomalous dimension. But for fermions, many times people just define the, let's call it eta psi. It's just the units to the field. It's basically 3 halves. Good. Now let's go to our interaction. Tree level of the interaction. So our interaction. So when we talk about the tree level, we're talking about slow slope. Only thing that we can call it S interaction shwai shwai. Okay? minus lambda to lambda dkg prime by minus omega to omega d omega prime over 2 pi. And then this guy comes with 1 over b to the 6th, right? Because we have 3 from here and 3 from here. Then we have an integral from 0 to 2 pi d theta. Okay, we have just 1 theta here, right? And then I open it and I have like f of theta psi bar 4 psi bar 3 psi 2 psi 1. So this guy, okay, let me just write, and then I have the plus v of theta. Now, when I write these terms, f of theta and v of theta, the theta is something different for each one of them, corresponding to these cases. And yeah, I didn't mention that actually for spinless fermions like we're looking at right now, there is actually only one f, because you can reach case 1 and case 2 by exchanging the fermions. Okay, so we actually have in this case only 4 terms, 2 terms. Okay, so I wrote a very compact notation, but you understand that this f and this v, they mean that the 3, the 4, 3, 2, 1, 4, 3, 2, 1 relate to case 1 and case 3, respectively. Okay, what?
Why you have just one angle and not 2 angles?
Because you said so yourself that the only thing that is important is the relative angle between the two. The other angle I can just integrate over. You're saying maybe I need to. Yeah, no, you're right. Wait a second. Probably there's another angle. Wait a second. Let me think about what you're saying. You're saying basically theta 1 is equal to theta 4.
Oh, you know what? I think you can do it with the angle between the two
yes.
scattering.
No. That okay. For sure, this theta is the relative angle between the two. But you're probably right that these guys. So there's like the relative angle, which I'm integrating over. But then there's also the sum of the two.
Maybe it's symmetric.
No, it's not. No, the fields. You're right. So I need. Sorry. So you're right. So let's do an integral 0 to 2 pi d theta, and then let's call it d phi. And phi would be, and then theta would be something like theta 1 minus theta 2, for example, in this case. And phi would be something like theta 1 plus theta 2 over 2. Okay? And then here, theta would be theta 1 minus theta 3, I guess. Theta 1 minus theta 3. And then phi would be theta 1 plus theta 3 divided by 2. Yeah, thank you. I need 2 integrals here. But it's not going to change this counting, okay? So then this guy comes with b to the 3/2, right, to the 4, because I have 4 fields.
Right.
So
Okay.
3 over 2 times 4 is exactly canceling with the 1 over b to the 6th, which means that these interactions are marginal at tree level. Okay, and this is a 4 fermion interaction for a Fermi liquid in any dimension. This is the beauty of Fermi liquid, that it doesn't matter what the dimension is. It's not going to change the fact that the interactions are marginal. Okay? So now let's do the calculation of the one loop corrections. So basically what I found.
What do you mean by marginal?
So when we look at when we do the RG,
yes.
we do it. We first do this is called tree level RG. Tree level RG just means that I stretch. So I'm looking at S shwaye, okay, and only looking how it changes under the RG transformation. Not looking yet at the other piece. So I remind you that the equation that we have is that S prime is equal to S0S, right? Plus, say, prime, maybe, I don't know. Okay, S interaction. And then these, we prime them in the sense that we make the transformation. And then we have minus the expectation value of, minus ln of the expectation value of minus SF interaction 0, right? So we have this part, which is all the diagrams and stuff, and this part is just the tree level. So this is like tree level.
And it doesn't change.
So at tree level, you can have three types of behaviors. One type is where it's relevant. So say I have a coupling J. So say the JDL is larger than 0. This is what we call relevant. So I remind you that L, so B is e to the L. Okay? So that's the connection, okay? So if the J, the L is smaller than 0, that's what we call irrelevant. And this distinction is very, very important to us because what it implies, typically we saw that, for example, in the phi to the fourth field theory, we want one thing to be like a tuning parameter of a phase transition, for example. So we're fine with it being relevant. But otherwise, if something is relevant, it's telling us that, you know, it's flowing away from this fixed point. This fixed point is no longer a fixed point. Okay? If it's irrelevant, then we have a justification to neglect it. You can forget about it. And in between these two, there's the limit where the JDL is 0, and that's what we call marginal. And that's the limit where we need to turn to this guy to understand what's going to happen. Okay? And what we find is that this is the case.
And J is like the tree level?
J, no. J is like a generic coupling. This was like a reminder because you asked a question that takes us back to like
lecture 1.
Yeah, it's like, you know, in the kindergarten when the teacher wrote Shalom Kita Aleph. So the next thing she discussed was like marginal and irrelevant, and I needed to like if it could be funny if like Eretz Nehederet would do a skit about our class, and then we would have a scene where Tzvi is taking us back, and we start from like super like integrals and diagrams and stuff, and at the end I'm like Shalom Kita Aleph, and then Tzvi is like, okay, this I agree. Okay, let's continue from there. Okay, this is not that strong. One of them was strong. God, it's getting worse. אולי זה בסדר. Let's try with this. Okay, so now we want to do the one loop RG, and I want to start from V. Okay? V is more interesting. Just throw everything. So I want to point out that V of theta 1, 3 is equal to V of theta 1, 4 plus pi, which is equal to minus V of theta 1, 4. What it means is that you could imagine that I switch between two of these guys and then relabel things. Then it's exactly so. First of all, okay, let me explain what I mean. So I want to remind you that what we have is an antipodal situation like this, where this is like 1 and this is 2, and then this would be like 3 and this would be 4. So if this is like theta 1, 3, okay, this angle here, then theta 1, sorry, this is theta 3, 1 actually. Oh, I always make this mistake. Let's put 1 here, let's put 3 here, 4 there, and 2 here, just because I don't want to draw big angles. And this is like theta 1, 3. Sorry, this is theta 1, 3. And then theta 1, 4 is just like adding pi in this case. So that's this connection.
But this is just when 3 correlates to 4, right?
What?
This is just when 3 correlates to 4.
Yeah, that's V. I'm talking about V.
Oh.
Okay? Case this is BCS. Okay? So now this piece is a different piece because sorry, this connection here is due to Pauli exclusion, because imagine that I relabel things and I call this 4 and this 3. Okay? And then I want to bring it to the same shape, so I just exchange their places. But then the only place where anyone would notice that I made this change is here in this V. So what it implies is that this V basically has two parts to it. It's a symmetric part and an anti-symmetric part. But the anti-symmetric part would just fall out, because I could rearrange. Maybe let me try and make that concrete. What I'm trying to say is that imagine, what?
It's like you multiply a matrix by an antisymmetric.
Yeah, you can think about it that these guys provide an anti-symmetric structure, and we're integrating over these angles. So the only part of V that survives this integral is the anti-symmetric part. Okay, good. So now so what we want to compute is the first second order in the commutative expansion. So we're basically talking about this diagram. which is equal to the expectation value of v theta 1 4, v theta 6 7, psi bar psi bar psi 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 bar psi bar psi psi 4 3 2 1 8 7 6 5 with respect to 0, where I connect between the vertices. If I connect within the vertices, remember that that gets cancelled due to the cumulant, because we're that's like re-exponentiating the first order. Okay, so that's one thing. Now the point is that this anti-symmetrization business. Okay, what I wanted. Okay, let me first say that. So the point is that we can imagine contracting this in two different ways, right? So I can contract, for example, between them. So first of all, notice that this structure of this V diagram is where I have two incoming, okay? Then so two connecting into the high energy states. These are like high energy. Fast, let's call it fast. These are like fast modes. So the point is that the fast modes need to connect two incoming to two outgoing, like this. Okay, what I'm trying to say, these are like the two incoming, and these are like the two outgoing. No, the other way around. Sorry, this is
You can have 1, 2, 3, 4 to be the upper.
Yeah, what I'm trying to say is you can do it like this, or you can do it like this. And what you're saying is that you can actually have the same two contractions also with these guys. Okay? But the point is, yeah, and then this is like 4 and 3. And this is like 6 and 5. For this specific combination that I look. And you can also switch between them, but that's not what's important for me. What's important for me is that you'll notice that these two have a minus sign relative to them. But all I wanted to say is that this minus sign actually cancels out with this anti-symmetric property. So all this argument with the anti-symmetry and the ways I can contract them is just to say that I can just look at one contraction and then count the symmetry factor, because all the other ones will give exactly the same thing, and even those that seemingly give a minus sign, if you remember that V also has this symmetric property, will give the same. So now we can use Tzvi's technique to count the symmetry factor. So I have these four kind of incoming and outgoing, okay? And then I have like two vertices. So the vertices have incoming, outgoing, outgoing. And then I can kind of connect, say, this here. So notice that I can connect it at two locations and also connect it to two legs. So I get a factor of 4. Okay? Then this guy has to connect to the same thing, so I have no choice here.
Why just 4?
Because they have direction.
Because they have a directionality.
Oh, okay.
Okay, good. Okay, now I now remember that I forgot to remind you about something, but okay, one moment. So, okay, this is fine. Now, these guys have to connect here, so here I have a factor of 2, and then this guy has no choice. Then this guy gives me another factor of 2, and then this guy has no choice. So overall, this is what you get. Now I pedagogically made a mistake because I forgot to remind you in the beginning of the class that the way we define the interaction at the U level comes with, so first of all we have a factor of 2 from the cumulant expansion, but then we also had this 2 factorial, if you remember, squared in the interaction, and here we have 2 interaction vertices, so it's to the 4th. So this is actually 2 factorial to the 4th, so the symmetry factor is 1/2. That's all. Okay? So that's a long story to say that this diagram comes with a factor of 1/2. And now let's calculate the diagram actually. So as we always do for RG, we're going to assume that we're going to neglect the incoming momentum and the outgoing momentum. Okay?
I think we have like another diagram. Maybe if you...
There is another diagram, but I'm talking about the renormalization of V. Okay, so the renormalization of V, I remind you that 6 and 5 need to be antipodal, and 4 and 3 need to be antipodal.
So they need to be with the same V.
What?
So 3 and 4 must be with the same V.
So here also, these guys are going to be also antipodal. Okay. Exactly. That's the point.
You're doing this just for the BCS channel?
Just for the BCS channel.
And the 2 there is from the LAN expansion?
This 2.
Yeah.
Yes. So then what I find is that the delta V of theta so we have something like, I don't know, 5, I guess 5/3, right? Okay, in this case is minus, by the way, this minus here is also coming from the cumulant expansion, because this is the second order in the cumulant expansion. So when you take the second order, you lose the minus sign, okay? But then there's an overall minus sign. Okay, so we get minus 1/2, and then you have an integral from minus infinity to infinity d omega over 2 pi, an integral over the k between lambda over b to lambda dk over 2 pi, and then an integral d phi from 0 to 2 pi. And then we have v of this theta 5 minus phi, v of phi minus theta 1, not theta 1, theta, what was it, 3. And then this whole thing is multiplied by g of omega and k, g of minus omega and minus k, which are these contractions here, okay? And I want to remind you that g of omega and k is just 1 over I omega minus Vf times k. So this we can calculate very easily.
Shouldn't we have more functions because we have 4 controls?
Oh, we have also an integral over d phi over 2 pi. No, we actually have only 2 contractions here because we're looking at the renormalization of the interaction. These are fast, these are slow, so we're not integrating.
They cancel out.
They don't cancel out. We're looking at, so I want to remind you what the philosophy behind RG is. We're integrating over S slow fast, the part that connects between the slow sector and the fast sector. So half of it is going to be slow and half of it is going to be fast. The slow modes are there because we want to reabsorb this correction into our interaction. So this means that these outer legs 6, 5, and 4, and 3 are slow modes in this contraction. And the internal modes are fast, which we're integrating over. Okay?
Yonatan,
Yes.
don't we are missing a master? Here.
Master.
The mu.
No mu. Because K is relative to the Fermi surface,
Okay.
right? But that's a technical answer. That's not the right answer. The right answer is the physical answer. That you know that on the Fermi surface, when you take K to 0 and omega to 0, you want the divergence there.
Right.
If I would just add here a constant, it would shift the location of the divergence.
Okay.
And K equal to 0 is exactly on the Fermi surface.
Okay.
Right?
Right. Sure.
Okay. So now you see that I have a problem with this V dependence. But I can always write V, I can write a V of theta as a sum over M being odd in this case, Vm e to the Im theta, right? And then if I do that, I find that the integral from 0 to 2 pi d phi over 2 pi V of theta 5 minus phi V of phi minus theta 3. This guy is nothing but sum over M e to the Im theta 1 4 Vm squared. Right? So then we can say that what we're actually looking for is not the correction to V of this angle, but to the angular the decomposition of V into harmonics.
Like if it was in 3D, you're basically using the summation of the harmonic spherical.
Yeah. So if this would be 3D, then this would be like a solid angle integral over the sphere, and then the decomposition, I would have to use spherical harmonics.
Okay.
Exactly. And then I find that this is Vm squared over 4 pi squared, the integral from minus infinity to infinity d omega, the integral from lambda over b to lambda dk. Here I use the fact that this expression is symmetric for k and minus k. So I eliminated this 1 over half with the integral over the cutoffs, above and below the Fermi surface. And then I just have 1 over omega squared plus vfk squared. And this is a very simple, it gives us a logarithm, this integral. The logarithm of, basically logarithm of b, right? Because it's between, the upper and the lower cutoff. And this integral gives us a factor of pi. So what we overall find is that dvm over dl, which was marginal at tree level, is just minus Vm squared over 4 pi. This is the equation for V. So V flows under Rg, and what we find is that it has the following flow diagram. So first of all, we find that each channel Vm flows separately. The reason for this is because we have angular momentum is a good quantum number. So the Green's function of the fermions doesn't mix between different angular momentum channels, and each angular momentum scattering channel is separate, and each one of them flows exactly the same way. So here we have Vm equal to 0, and then the flow, if we have a repulsive interaction, then it just flows to 0. And if we have an attractive interaction, right, it flows to negative infinity. Okay? So what we see here is that if we have a repulsive interaction, then it tends to disappear, and the Gaussian fixed point. Which is not Gaussian, as we will see. It's actually Fermi liquid. So the Fermi liquid fixed point. Actually, why not call it for what it is? Let me call it.
So that's the instability under attractive interaction.
What's the question?
That's the instability under attractive interaction. That's what
It's called BCS instability.
Yeah. Okay.
It's the instability to superconductivity. Okay? So what happens is that if we have even a small infinitesimal interaction, it tends to grow. And we can also solve this, the RG equation. So if we assume that L is log of B, which is log of, say, lambda naught over lambda final, okay, then we find that this thing, the solution, is Vm of 0 divided by 1 plus Vm of 0 times log of lambda naught over lambda final. Okay, and this is a very, very important expression. By the way, I should mention that this RG equation, exact same RG equation, appears in many different problems in physics, including the Kondo problem and asymptotic freedom. For the strong force. Okay? Not strong. Probably strong force.
I'm not that influenced.
Okay, no, I'm just kidding. But the point is that if you look at this thing, so you see that the interaction is renormalized with a logarithm, and it means that when you start from Vm of 0 starts attractive, this log just grows and grows and grows and goes to 0 as you go to lower and lower, as you lower this cutoff lambda f. But if it's attractive to begin with, then this Vm is negative, and then there's a point where this denominator explodes. There's a cutoff where this denominator explodes, and let's see what that cutoff gives us.
Yeah, a couple of. We show like so there in the middle board on the upper side on the right. It's not phi 14. It's a theta phi 3, right?
It's what?
It's theta phi 3 on the upper. Yeah, just want to make sure. And why is it this integral is ln if it's k squared? And why?
No, because you do the integral over omega, you get
First, okay.
1 over k with a pi. And then the integral over k gives you a log.
Okay, you do first omega. And I'm not sure I understood like what's his lambda naught and lambda f. Like,
So when you
B
do
is
RG,
like
the philosophy behind RG
Yes.
is that you start at a specific scale
Yes.
and then you stop at a specific scale.
Yes.
So lambda 0 is the initial cutoff,
Okay.
and lambda final is the final cutoff.
Oh, like, do they have like?
Yes, they have very physical meanings.
My
For
meaning.
example, let's assume that you have a finite size sample. So, for example, Hanan was asking me, he wants to do experiments with small, samples. And he's asking me, how big does the sample need to be for it to become superconducting? So we can use this RG way of thinking to answer Hanan. Let's answer Hanan now. How large the sample needs to be in order to see superconductivity.
Okay.
So in order to see superconductivity, we know that this interaction needs to diverge. Okay? So let's see when that happens. That happens when when this absolute value of Vm, okay, of 0, okay, is equal to minus log of lambda 0 over lambda f. Okay, where lambda 0 is the microscopic scale, and lambda f is after a lot of coarse grains. So I can rewrite this thing actually as because this is a momentum scale, I can rewrite this as xi over a. So a is like the microscopic cutoff, and xi is the large scale. Okay? And then I exponentiate everything. So I get that e to the Vm. Wait, did I do this correctly?
E to the minus.
No, actually, no. What I need to write is this. Sorry. It's 1 over Vm. Because, you see, they're multiplying each other. So this, I claim that when this happens, assuming that Vm is negative, that's where this interaction diverges. Okay? Now I exponentiate everything, and I get that xi goes like a e to the minus 1 over Vm. Sorry, not 1, minus, like this. Okay? So this is what is known as the coherence length of the superconductor. Now you could also ask the same question about temperature. So you could assume that what cuts you off here, lambda f, is a low energy temperature, and that this upper cutoff is where the attractive interaction starts. That's omega de pi. So then this equation would become 1 over Vm, okay, of 0. By the way, this is Vm of 0. This is like the original thing. Is log of omega de pi over Tc. So this would be the temperature at which the instability occurs. And this gives us the famous equation for BCS, which is omega de pi e to the minus 1 over Vm. Okay, which is another thing.
What did you see here? Like
the point where this interaction diverges.
Then what?
Then something happens.
Then something happened. And in the second example, what happened?
What?
In the second example, what happened? Like what we are seeking?
No. So here we said, let's ask how large the sample needs to be to start seeing superconductivity. And the conclusion is that it needs to be larger than the coherence length of the superconductor. Here I'm asking at what temperature. I'm thinking about these cutoffs as energy.
Okay.
Because I can associate momentum with energy, because this is I forgot to mention the dynamical critical exponent. So I wanted to say that this is a bit different than what we did. Remember that when we did the RG for the phi to the fourth field theory, we had a sphere. Here we're not doing a sphere because frequency is going from minus infinity to infinity. and we're doing something like a strip. It's more like a strip RG. But these are just different techniques. They should give the same result. Presumably, we want our G method not to depend on how we define these cutoffs. But the point is that once we have frequency and momentum on a different footing, then there is like scaling. When omega, we can rescale it. Well, you'll see that once. Okay, I gave you a taste. I can't give you more than that. Okay. I'll just give up on this thing. Okay, but no, there is some comment about what is a dynamical critical exponent, but here we're thinking about a system where omega and k scale the same way. So energy and momentum would scale the same way. So I can think of omega naught as like the high energy cutoff, which would be omega debye in the case of a superconductor, and lambda f, the final, is the temperature where it diverges.
Okay.
So you see that you get the expression for BCS, the BCS result, and this is just our G. It was very easy. And now the last thing I want to say, okay, with the 10 minutes I have left for this course, is to talk about the renormalization of F. So the point is that in this case, you can convince yourself that the kind of diagram that we have is where these guys are equal, right? So like 1 and 4 are like the same angle, and 5 and 8 are like the same angle, and then these are like low energy, and these will be like high energy. So we have an integral over phi of theta 1, 2, theta 6, 5, psi bar, psi, psi bar, psi bar, psi, psi. And then we have 4, 3, 2, 1, 8, 5, 8, 7, 6, 5. And then the kind of connections we're going to make, it's the same story as before. We can just look at one of them, but basically we connect, say, this to that, and say this to that, something like this. And 5 to 6. So then it's related to what I just drew here. And you can do the symmetry factor and discover that the symmetry factor is 1. I won't do that here because there are more combinations in this case. But basically what you find is that delta F theta 5 1, which is what this renormalizes, right? 1 and 5, you see, 1 is equal to 4 and 5 is equal to 8 in this case. So the only angle we have is between 5 and 1. And this guy is an integral between minus infinity to infinity, the omega over 2 pi. The integral over k, which is between lambda over b and lambda, dk over 2 pi. And then we have an integral over some angle d phi of f of theta 5 minus phi, f of phi minus theta 1. And then the point is that if we neglect the momenta, incoming this diagram, then we basically have just the square of two Green's functions with the same momentum. Why do they have the same momentum? Well, they have the same momentum because in this case, what is incoming is outgoing, and what is incoming is outgoing. So we have basically 0 incoming momentum. So, or another way to view this is is that now these two Green's functions are not going in the same direction. They're going in opposite directions. So the result of this is that these G's, unlike before, unlike here, we have two G's that have poles on the same side of the complex plane. And you can convince yourself that this gives 0. This contribution gives 0. The reason is because we're integrating over a shell. So you might identify that this actually is very similar to when we calculated the polarization bubble. But the contribution to the polarization bubble comes from low energy. Because we're doing a shell here, in this case, this contributes nothing. We get 0. So what it means is that basically F remains marginal also in the one loop order. And in fact, one can argue generally that because you're always forward scattering, right? The whole point is that in each one of these processes, you're kind of forward scattering. So these are very, so if these are like 2, then these two are equal to each other. These two are equal, and you get all the poles on the same. So you can make this diagram more and more complicated, but you'll always get stuck with the poles being on the same side. And that implies that F is actually marginal to all orders. So that means, what it means is that basically for each set of F that you get, they remain invariant under the RG. So they're part of our fixed point action. And that's what we call Fermi liquid. And then...
It means that superconductivity can only occur in the BCS channel.
Well, it means...
It
means... Okay. What it means that the Fermi liquid theory is basically stable or remains a fixed point. Okay, I didn't write what Fermi liquid is. So let me first write what Fermi liquid is. So I didn't teach you Fermi liquid theory. But there is such a theory which, you know, it turns out that the Fermi golden rule was first derived and understood by Dirac. And Fermi liquid theory is, you know, an ingenious idea by Landau. So I don't know why they call everything Fermi, 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 but so the idea is that you can think of a free energy which is a function of density in momentum space. So delta NK would be a difference with respect to the mean plus 1/2 sum over k and k prime, f of k and k prime, which are these forward scattering terms, delta nk, delta nk prime. So the point is that, you see, they come in pairs that have the same momentum. So this thing was laid down by Landau to explain Fermi liquids. How did he know? Now, these f's, f of k and k prime, you can write as a sum over m equal to 0 to infinity, vm e to the I L theta of k and k prime. Not v, sorry, f. What am I saying? F. Okay. Now, how on earth did Landau know that this is what you need for this fixed point? Only God knows. He is genius. He is brilliant. Okay. So he basically, Landau almost single-handedly, not single-handedly completely, but almost single-handedly laid down the two foundations we have to understand: fermions and bosons. The Ginsburg-Landau theory for phase transitions and bosonic systems, and the Fermi liquid theory. This. And what this RG calculation shows you is that this is indeed the fixed point. So I didn't teach you Fermi liquid theory, but if you open a book, you'll discover that starting with this theory, you can derive a lot of stuff. And basically the behavior that you're going to get is going to depend on these F's. So there is an infinite number of F's. There is a Fermi surface size defined by mu. There is a Fermi velocity defined by this epsilon, and a mass, basically. And there is another parameter that doesn't appear here, which is known as the quasi-particle residue, which is the overlap between these quasi-particles and electrons in the vacuum. And these parameters define completely the Fermi liquid fixed point. So what we've seen and learned today is that the Fermi liquid is stable to all kinds of interactions, except attractive interactions in the BCS channel. So actually that's not entirely true, because that's only true for weak interactions. That's a weak coupling statement. In a strong coupling statement, these F's can also cause instabilities, like Stoner instability and Pomeranchuk instability and all sorts of other instabilities, CDWs and stuff. That can happen. But that's not a weak coupling instability. So the Fermi surface is stable to weak perturbations, except the BCS scattering. And as long as you're not going in that direction, then all the other perturbations, these F's, are marginal to all orders. And then you just, like, this is what you have. You don't have I misused the word F. Let's maybe make a fancy F. Okay, this is the free energy. So what it means is that what does it mean? It means that it means that you have this set of infinite number of it's called Landau parameters. These are called Landau parameters, and they define our Fermi liquid. And then, to make things interesting, to end, I think it's a good way to end the course, is to tell you that in the 60s, Kohn and Lattinger wrote a paper where they noticed that the interaction between electrons in a metal is non-analytic. Okay? Why is it non-analytic? Because of the screening. So we learned about the self-energy correction to the interaction. This self-energy of the boson, this pi, the polarization bubble, is non-analytic function. And as you've learned, well, Joseph didn't learn math 3 with me, but you two did. As you've learned in math, a non-analytic function, if you Fourier transform it, it's going to have an algebraic tail, right? So if we assume that the regular part of the interaction, the part before the renormalization, is some short-range thing, then typically we have the original interaction is going to decay exponentially in some sense. But the non-analytic correction is going to have this algebraic tail. And then the last piece of information, and this is the crucial thing for Kohn and Lattinger, is that the Fourier components of this non-analyticity tend to have this alternating sign, plus, minus, plus, minus, plus, minus. What that implies, it implies that at a large, now remember that when we're doing Fourier transform, I wrote here L, but it didn't stop me. Is it N? So the point is that these components M are now my Fourier space. So the same structure like you have in Fourier space, what you're going to have is as you go to larger and larger M, these polarization, the Fourier transform of the polarization bubble is going to decay algebraically with alternating sign, and the pair interaction is going to decay exponentially. And as a consequence of that, what happens is that at a high enough angular momentum, you're always going to have attraction. Okay? And that's crucial because it means that a Fermi liquid is always unstable. Okay? Because even if it's a repulsive interaction, and naively you shouldn't have attraction, at a high enough angular momentum channel, because of this non-analyticity of the polarization bubble, it's always going to develop attraction. And then it's always unstable at a low enough temperature. So an open question, which is hovering over condensed matter physics always, is whether a zero temperature metal is a phase that even exists. Okay? Because you can try to evade in all sorts of ways, but okay, that's a different question. But I won't get into that. But the basic point is that the Fermi liquid is basically always unstable due to this Kohn-Lattinger argument.
This is what people mean when they say that superconductivity is the most boring case because
yeah,
it
that's
always
what I was,
will emerge.
Yeah, so then that's what I was probably you heard that from me,
Yes.
probably.
Yes.
But yes, it's related to this issue. That basically, if you look at superconductivity from this viewpoint, like superconductivity when it was discovered was this astonishing phenomena, surprising. But once you understand this RG point of view, you suddenly understand that actually the only way to destabilize a Fermi surface, a Fermi liquid, from the weak coupling perspective is through superconductivity. So it's almost inevitable that it will become a superconductor at some temperature. Okay?
Provided that the mechanism of attraction exists.
No, that's exactly the point. The point is that it always exists.
No, but in this case it's because of the angular momentum.
Yeah, but this angular momentum dependence is generic. It always exists.
Right.
There's no way to avoid it.
Okay.
That's the point.
And another question. Anytime I see, of course with weak interaction, but anytime I see something which is non-Fermi liquid, even if it's not in the superconducting phase, it means it's a BCS current, BCS channel?
No, because that's what we said. We said that all this is a weak coupling argument. You have to remember that the RG assumes that these couplings are weak.
Okay.
Right?
Yes,
First, in a few different places we use that.
Yes.
First of all, when we computed the corrections, we integrated out fast modes and we used only their Gaussian part.
Okay.
Okay. And the second thing is that within Fermi liquid theory, you can also show that it is only stable in the weak coupling limit. And RG in general, this expansion in loops, well, here we didn't really need that, but in general, the RG method is assuming a weak interactions, and we're expanding around some fixed point. But in this case, you're right. It's a little bit more delicate because I could stretch much more, because the Fermi liquid can have significantly large Fs and still be stable, and I can still do the computation with just correcting, I just need to remember to correct everything which I didn't do with, quasi-particle residues, effective mass, blah, 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 all these business. If I assume to do that, then I'm fine.
Okay.
What does angular momentum, like high enough angular momentum, means in scale?
In scale?
Like at which point?
What do you mean?
You said like at the angular momentum.
So maybe let me make that a little bit more concrete so it'll be clear. What I mean is, okay, one way you can think about it is that let's look at our interaction. This is like our interaction as a bare interaction plus the bubble. Okay. Then this bubble, then this is like u plus u squared times pi. Okay?
Okay.
It's actually more complicated than that. You can ask Amir. Because, okay, you know what? Let's make it rigorous. To make it rigorous, let's actually consider an interaction like this in the density channel. Then I can rewrite this as this plus this plus plus okay, this one is going to be most difficult for me to draw. I think it's wait a second, remind myself. So it's typically like this. Exchange. Okay, maybe I'll just exchange it like this. It'll be easier. So I can do something like that. Okay, so if you and so on and so forth. So it turns out that if you calculate this, then this, and this cancel for a contact interaction, short range interaction. You stay only with this. And then it's actually with the minus, if you really want to be, but never mind. Not such sorry, it's actually with a plus. Sorry, this gave you a minus.
Yeah, okay.
So it comes out with a plus, and that's fine. But the point is that now you could imagine that this u is not exactly delta function short range, but it has some finite range. So it has some weak Q dependence, which we neglected in this cancellation. And then you can do a Fourier transform like this in angular space.
Okay.
What you'll find is that because this is a non-analytic function of the angle between them, okay, and this guy is, you'll actually find that the components um of u and the components pi m of pi, okay, the ones decay like exponential, and the pi m ones decay algebraically because of this non-analyticity, and they also always have negative signs. So that means that if you go to a large enough m, because one of them decays exponentially and the other one decays like a power law, there's going to be a large enough m where one overcomes the other and you get a traction.
Okay.
And this is inevitable. That's the point. So it's a very profound paper. If you connect all these pieces together, like Fermi liquid theory, with this RG picture, and then with the Cohn-Lattinger, all together, you get this whole view of what's going on. It's very, very deep. Okay?
Sure.
So it's a philosophical question, if you like, whether or not such a thing even exists, like a metal at zero temperature without breaking time versus symmetry, without disorder. I don't know. There are some. Yeah. Okay. I survived.
אנחנו שרדנו.
תודה רבה.
שרדתם.
אגב, זה... אין שם דלתא מיו, דלתא R.
דלתא מיו, דלתא R.
דלתא M? אין.
מה זה דלתא?
זה אין.
סטייל כזה, כן.
אוקיי.
סטייל פסאי בריבוע, פסאי ברביעית כזה.
כן. נכון.
על מה אנחנו מדברים?
סתם על הפרי...
באנרגיה החופשית שיש דלתא, ואז משהו שנראה כמו N או M או מיו. הכוונה היא N, נכון?
אתה שואל מה זה?
כן.
דלתא.
דלתא?
דלתא N. דלתא N של K זה כמו C דאגר K, CK מינוס הממוצע שלהם, C דאגר K, CK. עכשיו, הרעיון מאחורי החבר'ס האלה זה שאתה רואה שב-F channel, הרי אמרנו, נכון, שב-F channel אתה צריך שהם שניהם יהיו באותו כיוון. נכון, נגיד 1 ו-4.
כן.
אז אתה באמת מקבל פסאי דאגר פסאי שהם אותו K, ופסאי דאגר פסאי שהם נגיד K אחר. אז זה ה-K ו-K פריים. זה ה-forward scattering terms.
אגב, היה 3 תנאים, נכון?
כן. את התנאי, יש תנאי של exchange, שאני לגמרי זנחתי אותו פה, כי אין לנו ספין. כשאין לנו ספין הוא לא נהיה בעל חשיבות, כי הם בעצם מתמפים אחד לשני. אתה יכול לכתוב את שניהם, אבל אז אתה יכול להחליף ביניהם, לעשות ריניימינג, הם יכולים להיות זהים.
כן, סבבה.
זה פשוט השתיים שהתבטל עם החצי, אכלנו את זה בתוך 0, 2, נכון?
2?
למרות איזה פקטור כזה.
כאילו היה לכאורה אמור להיות...
אתה שואל על הסימטרי פקטור?
כן.
לא. סימטרי פקטור עדיין גדול יותר, גם כשאתה...
גם אם אני מחליף.
אבל מה זה משנה אם זה 2 או 4 כפול 0?
כן.
אני אתרום את הטושים. אתם מכירים את זה ששחקני כדורסל או שחקני טניס נגיד, אחרי המשחק הם זורקים לקהל את זה, אולי נזרוק לכם את הטושים?
זה עובד?
חצי, מה זה משנה? אתה תוכל לספר שזה הטוש שאיתו למדת בקורס קוונטית פילטרי, שהוא אגדה. פיינמן היה מקנא בכמות הסטודנטים שבאו לשבת פה על המדרשות.
דווקא זה שיש פחות סטודנטים זה קורס יותר...
זה עדיף בפעם. יש
קורלציה.
לא, אתם יודעים שאומרים שאצל פיינמן, כאילו, אחרי שהוא הפך להיות מפורסם, אז הוא היה מעביר קורסים, ופשוט, לא יודע, סטודנטים לסוציולוגיה היו באים לשמוע, לא יודע, כל העולם היה מפוצץ עד 0 מקום כל הזמן. בטח 90% מהם לא הבינו על מה לעזאזל הוא מדבר בכלל, אבל וואו, זה פיינמן. כן.
זה עדיף שיש קצת סטודנטים.
כן.
מה היה המרצה הכי אגדי בהיסטוריה של האנושות?
למה?
מה?
למה?
ככה לא יודע. ככה אומרים. תשמע, קודם כל הוא היה אגדה עוד בימי חייו. הוא היה נחשב למרצה הכי טוב. וגם הוא ידוע, כאילו, בתור מישהו שמסוגל להסביר. אתה יודע, הרי זה משהו כזה, האם אתה מסוגל להסביר משהו שהוא נורא מסובך בצורה שאנשים יוכלו להבין. זה כאילו איזושהי יכולת של פיזיקאים שהם מאוד מאוד מחשיבים אותם. ואתה רואה הרבה באמת קורלציה בין פיזיקאים שמסוגלים להסביר בצורה כזאת להצלחה. יש את זה בהמון מקומות.
זה מעניין, כי זה כאילו סוג של קורלציה בין מחקר ללהיות מרצה.
נכון, אבל
כל הפרופסורים אוהבים אותה.
לא לכולם יש אותה, ויש הרבה מאוד פיזיקאים מעולים שאין להם את היכולת. אבל אלה שהם במיוחד טובים בזה, הם תמיד גם, לא יודע אם תמיד זה קצת מילה חזקה.
זה זווית מספיק.
תודה רבה.
בבקשה.